Welcome to the Insightful Professor. In this video, we'll continue our examination of type inheritance. In the previous video, we discussed the concept of inheritance and focused largely on application programming language such as Java to introduce terminology and concepts. In this video, we'll continue our discussion by shifting toward object-relational database, discuss the SQL 1999 standard, and how the Oracle database product adheres to this standard. We've previously discussed the create type statement. This statement is used to define a user-defined type. What we have not talked about is a special clause. There's an option of final, or there's an option of not final. The default for this is final. And what that means is when you create a type, that's as far as you're going. That type cannot have any subtypes. The examples we've presented in earlier videos have all taken the default of final. This means that those types could not have subtypes created for them. And that was fine based upon what we were presenting at that point. What we need to do is explicitly specify not final in order to have this play a role of being a supertype and be able to create subtypes below this or under this type. We can also create a type using a clause called not instantiable. This is the idea of creating a type for which you'll never create instances, but from which you'll inherit certain properties or characteristics to define subtypes. It's similar in a way to the Java abstract class concept. In our earlier videos, we provided examples where we assumed the default of instantiable, and as a result, we were able to create objects of that type. The Oracle object model does not define a master root level class, as we saw with Java. Java has a special class called Object, from which all other types that you define will then inherit. Here's an example of creating our friend the address type. We say create or replace the type as object, and we define the attributes. We can then issue a SQL+ describe command and review the structure of this object. If our intention is to use address as the root type in a type hierarchy, we must specify not final. Remember that final is the default and will prevent subtype definitions. Let's attempt to create a subtype. When we try to do this, what we receive is a warning. This type does get created, but there are compilation errors. It's effectively unusable. What are the problems? Well, with SQL+, we can use the command show errors from the command prompt, and this will reveal the actual error message. It tells us that we're attempting to create a subtype under a final type. Now, compilation errors can be examined in different ways. If you're using SQL+, this is the most convenient way to do a show errors command. But if you're using the Oracle Live SQL, the show errors command is not supported. What you would need to do is to execute a query against a table called user errors. When we execute a compilation of some PL/SQL code, a stored procedure, or creating a type, then if that code compiles with errors, then the errors are temporarily recorded in something called user errors. The show errors command will generate and execute a query for you against that table to retrieve the result. But if we're using Oracle Live SQL, then we have to write our own query. We could simply write a query that says select asterisk from user errors, and that would give us the gist of what's going on. We'll talk more about this as we go along. Let's take the code we were just examining and try it on the system. First, suppose we wanted to create the address type. We get the response, the type was created. Then we go to create the second type, which again is a subtype. And notice it says it was compiled, but we get the error. So SQL Plus requires that you execute the show errors command to retrieve the error information. SQL Developer presents it nicely to you in the output when you run the command. But we also could go and get this ourselves. We could run a query such as select asterisk from user errors. Let's clear the output and show you what we get. Now there's quite a bit of information presented here. You've got the name, the type, sequence and line, position, and finally you get over to the column referred to as text, and there's your error message. Among the metadata that is recorded for user-defined types is the dependency of a type. A type can only be dropped if it has no type or table dependencies. If the type is used as a column object in a table, all columns dependent on the type to be dropped are marked as unused and become inaccessible. To drop a supertype, force must be specified. Subtypes depending on this supertype are then invalidated. There's a view called User Dependencies that contains information about all the dependencies of the user's database objects. Also note that the drop type statement has a force option. That will cause the type to be dropped even though it may have dependent types and tables. The force option should be used with great care because any dependent types or tables that do exist are then marked invalid and become inaccessible when the type is dropped. Data in a table that is marked invalid for this reason can never be accessed again. In fact, the only action that can be performed on such a table is to drop it. So you may ask, why are we talking about dependencies and then suddenly dropping a type? Well, recall that we just created the address type, and then we attempted to create business address as a subtype. But we found that that didn't work because address was declared as final. So it's going to be necessary to drop address so that we can then recreate it with not final and then proceed to create a subtype. But remember, it did say that business address was created, but it compiled with errors. So that dependent type exists. So if we try to say create or replace address, and now add the not final clause, we get an error. And this tells us that you're trying to remove an existing type and replace it with a new definition, but you can't do that because something depends on this. What depends on it? Business address, even though it wasn't compiled, it was still created and the dependency was recorded in the database. So the create or replace type statement throws an error if the type being replaced has table or type dependencies. And that's exactly what the error suggests here. This applies to objects, V-arrays, and nested table types. This also applies to type dependencies involving either inheritance or type composition, which refers to the embedding of one type within another type. That could arise from one type being an attribute of another type. This is a useful query to remember. We can query user dependencies, and we can find out the name of an object of some sort, some kind of database object, and we can find out what dependencies might exist. So notice that business address appearing in the third row references address, which is a type. And despite the fact that business address was compiled with errors, that dependency still exists within the database. What we need to do is to first drop the subtype. So we drop type business address, then we go and create a new definition of address using the not final. When we specify not final, this will allow us to create subtypes. So now when we need to describe address, Everything looks the same as before, except it does announce that address is not final. So once again, we realize that if you're using live SQL, the SQL plus describe command is not available to you. So we can actually construct a query against user type attributes. And I'll put that up here. For numeric attributes, we would extend this query to also select precision and scale. So with the business address removed from the database and address created as not final, we can then proceed to provide a new definition of business address, making it a subtype under the address supertype. Then when we proceed to do a describe of business address, it tells us that business address extends address. And we have all of the attributes that we inherited, plus we have the additional attribute of mail drop, which we defined in our create or replace type statement here. We can now use our types to create object tables. So here we'll create the addresses table, which will be a container of row objects, each of which is an address. We can also create something called B addresses, which is a table of business address. As we proceed to do our describes, the structures of these two tables are revealed to confirm that they are indeed created of address type and business address type. We can then also populate the table. We can do an insert and invoke the addresses constructor or the B addresses constructor as appropriate. And when we do a select against the tables, we get our results as shown here. Now, if we query user types, what we see is we'll get the name of the type, we can get the attributes, and notice address has 4, business address has 5. Address is not final, but business address is. And they are both instantiable. And that makes sense because we just created an object of each type in our object tables. For supertype name, address has a value of null because it's effectively the root in our hierarchy. It has no supertype. But business address has a value of address in the supertype name, showing that dependency. And in terms of local attributes, well, this is where we're talking about a subtype, so it's not applicable for address, but for business address, we did add mail drop in addition to the attributes that we inherited, so we have one local attribute. If we query user type attributes, we can see for business address, we have the 5 attributes that we recognize here. 4 of them are marked as inherited because they were inherited from the association with address as the supertype. Mail drop says it's not inherited. That's the local attribute. The ANSI SQL 1999 standard uses the term most specific type to mean the structured type closest to the leaves of the type hierarchy of which the instance is a member. This is also the name of the constructor method used when the instance was created. The concept of most specific type is important because it means that you can store in a data type any value whose most specific type is that type or any of its subtypes. The ability to provide an instance of subtype at any location where an instance of a supertype is expected is called substitutability. The reverse, however, is not true. When working with types in a type hierarchy, you might need to work at the most general level, operating on the supertype. For example, you might want to select or update all persons. At other times, you might need to select or update only a specific subtype of person, such as a student, or only persons who are not students. This polymorphic ability allows us to select all persons and get back not only objects whose declared type is the supertype, it also allows for objects whose declared subtype is student or staff. A supertype is substitutable if one of its subtypes can substitute or stand in for it in a variable or column whose declared type is the supertype. An attribute defined as a ref, type, or collection of a supertype can hold a ref to an instance of or instances of the supertype, or an instance of any subtype of the supertype. This is reasonable because a subtype is just a specialized kind of one of its supertypes. In object-oriented programming, polymorphism refers to the ability of an object reference variable or an object pointer to reference objects of different types. Polymorphism means multiple forms. Formally, a subtype is a type in its own right. What this means is a subtype is not the same type as its supertype. They are related, but they are not identical. Taking this view, we can say that a column that holds all persons, supertype objects, including all persons who are students, subtype objects, and all persons who are staff, also a subtype, actually holds data of multiple types. So in principle, object attributes, collection elements, and refs are always substitutable. There's no syntax at the level of the type definition to constrain substitutability to some subtype. However, it is possible to turn off or constrain substitutability at the storage level for specific columns or tables. Earlier, we discussed dependencies and the replacement of a type definition using the create or replace type statement. We wish to note that a substitutable table or column of a specific type is dependent not only on that type, but on all subtypes of the type as well. This is because a hidden column is added to the table for each attribute added in a subtype of the type. The hidden columns are added even if the substitutable table or column contains no data of that subtype. If dependent tables or columns exist but contain no data of the type being dropped, you can use the validate keyword to drop the type. The validate keyword causes the system to check for actual stored instances of the specified type and to then drop the type if none are found. This also removes the hidden columns associated with attributes unique to that type. Let's consider the dependencies of the two objects that we've created in our schema, address and business address, and the tables that we've created in our schema, addresses and B addresses. We run a query against user dependencies, and what we want to point out in this output are the two rows that we've highlighted here. The two rows that have addresses as the name show for the reference name both address and business address. This is due to substitutability. Although the table addresses is a table of address, we could store business addresses there. Overloading refers to a situation where a type has more than one version of a function or procedure with a particular name. The process of overloading a method can be useful when there is more than one way of performing the operation. When a type has several methods with the same name, the compiler determines which version to invoke based upon what's called the signature of the method. The signature consists of the name of the method plus the formal parameters. So within a particular type, methods that have the same name but have different signatures in the sense of having a different arrangement of parameters or parameters of different type are considered to be overloads. In contrast, there's a concept called overriding. Overriding redefines an inherited method to make it do something different in the subtype. So that means a method defined in the supertype is automatically inherited by the subtype. The subtype can choose to keep that version as the one and only version, or it can provide a new definition of that. It can override the definition. So when a subtype overrides a method, the new version is executed instead of the version inherited that had been overridden. This happens whenever an instance of the subtype invokes the method with that name. In a complex type hierarchy where a subtype has subtypes, the subtypes inherit the override of the method rather than the original version. For a method to be overridden, its signature must be preserved in the override. That was one difference we saw with overloading. You're changing the signature in some way. But here, it's the same signature, but it's kind of like executing a local version versus one that's far off, the inherited version. We use the overriding keyword to specify in the type declaration and indicate the override of a method. As a result of method overriding, a type hierarchy can define multiple implementations of the same method. When a method that is overridden is invoked, the type of the object instance that invokes it is used to determine which implementation of the method to use. The method invoked is the one in the most specific subtype associated with the currently instantiated object. The call to this method is dispatched to the appropriate implementation for execution. The process of selecting a method implementation is called virtual or dynamic method dispatch because it is done at runtime and not at compile time. The following restrictions apply to overriding of methods. Only methods declared to be not final in the supertype can be overridden. Order methods may appear only in the root type of a type hierarchy and may not be redefined or overridden in subtypes. A static method in a subtype may not redefine a member method in the supertype. A member method in a subtype may not redefine a static method in the supertype. An overriding method must provide the same parameter defaults as the method being overridden. This concludes our introduction of inheritance concepts in the object-relational world. In our final video on this topic, we will work through examples using Oracle Database. We'll examine special operators that are used with substitutability of subtypes and supertypes.